Okay, let's try this again. So I just finished a beautiful 20-minute explanation for this question and had my program freeze as soon as I hit the end record button. So I'm not going to write all this stuff out again, but you guys can follow along. I'll explain my thought process and my work as I go. Okay, so when we look at this example number 3, this is the example that we closed out class with. So we're integrating x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x with respect to x. Okay, and there's a couple of things that we should see when looking at this. Number one, I can factor my denominator. So I can factor an x out at the start, which gives me 2x squared plus 3x minus 2. And then I can factor that quadratic to be 2x minus 1 times x plus 2. So the good thing I see is I can write that denominator as a product of non-repeated linear factors, which means it's going to be a candidate for partial fraction decomposition. But before I can do partial fractions, I have to check to make sure that the rational function is proper, okay? Which means the degree of the numerator is smaller than the degree of the denominator, which it is here. So that's great. Like I can jump right into doing partial fractions. If it's not, you would have to long divide the denominator into the numerator before you could do partial fractions. Okay, so when we look at that denominator, we see we have the product of 3 fractions. So, the product of 3 like linear factors. So I'm going to be able to separate that rational expression into 3 fractions. The first one being a over x, the second one being b over 2x minus 1, and the third one being c over x plus 2. Okay, so this just turns into an algebra problem now. So we can go ahead and solve this rational equation, multiplying both sides by our common denominator, which is going to be x times 2x minus 1 times x plus 2. And when I do that, on the left-hand side, it leaves me with x squared plus 2x minus 1, the numerator. When I multiply the common denominator by the first fraction, the factors of x cancel. So that leaves me with a times 2x minus 1 times x plus 2. When I multiply it by the second fraction, the 2x minus 1s cancel, which leaves me bx times x plus 2. And then when I multiply it by the third fraction, the x plus 2's cancel, which leaves me with cx times 2x minus 1. Okay, so again, I showed you like 2 ways to do this in class. If you try doing this the way that I learned as a student, boy, the problem gets really messy because you would have to like multiply everything out on the right-hand side, group the x squared terms together, group the x terms together, group the constant terms together, and then you're going to have to wind up solving a system of 3 equations and 3 unknowns. It's like that's going to be time consuming for you. Okay, so the second technique that I showed you, like the shorter, faster way, is really advantageous to you with this example. Okay, so if we want to solve for the variable a, we're going to let x equal 0, and the reason we want to do that is if x is equal to 0, this term here and this term here, so I put a line over the top so I can erase. If x is equal to 0, then the middle factor of both of those are going to wind up becoming 0, which is going to get rid of the b and c terms. Now, what makes this different from the example we looked at in class is like you have an x on the left-hand side of your equation. So you have to plug 0 in the place of x on both sides. So when we do that, the left-hand side becomes -1. And then that first term on the right-hand side is going to become a times -1 times 2, which gives you -1 equal to -2a, which makes a equal to 1/2. If we want to solve for b, so if I want to solve for b here, I'm going to let x equal 1/2 because that's going to make that factor 2x minus 1, the middle factor, become 0. And it's going to make this last factor 2x minus 1 become 0, which is going to get rid of the a and c terms. So when we plug 1/2 in the place of x on both sides and solve for b, we're going to get b equal to 1/5. And I showed the work for that. And then if I want to solve for c, We're going to let x equal negative 2 because the last factor of a becomes 0, and the last factor of b is also going to become 0. So that's only going to leave us with c, which we can solve for c. So when we plug negative 2 in the place of x on both sides of the equation, we get c equal to negative 1/10. Okay, so once you get those values of a, b, and c, you have two ways that you can proceed. Okay, so the way I work this out on the left-hand side, this is how I'm going to recommend you guys work the problem out, because I think it makes the calculus easier for you doing it this way. So we have the values of a, b, and c. A, b, and c are all fractions. So what I'm going to do, if that first term is going to be a over x, and a is 1/2, I'm going to break that up into 1/2 times 1 over x. If I take 1/2 and divide it by x, that's the same thing as taking 1/2 and multiplying by 1 over x. If b is 1/5, I'm going to pull 1/5 out in front of the second fraction, so that's going to be 1/5 times 1 over 2x minus 1. And then if c is negative 1/10, I'm going to pull negative 1/10 out in front of the third fraction, so that's negative 1/10 times 1 over x plus 2. And when we do this, we now have something that we can integrate pretty easily. So if we pull 1/2 out front, the antiderivative of 1 over x is the natural log of the absolute value of x. If I pull 1/5 out front, the antiderivative of 1 over 2x minus 1, like that's a composite function. You're going to want to do like u substitution for that, but that function is easy enough to integrate that we should be able to integrate it without doing u substitution. So that's going to wind up being 1/2 the natural log of the absolute value of 2x minus 1. Okay, so that's the natural log of the absolute value of 2x minus 1 divided by 2, or multiplying by 1/2 is the same thing. And then we pull negative 1/10 out front, and the antiderivative of 1 over x plus 2 is going to be the natural log of the absolute value of x plus 2. And then the last thing I did was just multiply 1/5 times 1/2, what I highlighted, and that becomes 1/10. So that's my first antiderivative. And that's how I would recommend working the problem out. Okay, but you also have another option where you can work like a, b, and c into a single fraction. Okay, so if you do it this second way, if you take 1/2 times 1 over x and combine that into a single fraction, that gives you 1 over 2x. If you take 1/5 and multiply it by 1 over 2x minus 1, that becomes 1 over 10x minus 5. And then if you take negative 1/10 and divide it by x plus 2, that becomes negative 1 over 10x plus 20, which you can integrate with respect to x. And again, like we can integrate that as well. I think the calculus is a little more complicated because you're going to have to, I mean, like technically you could do each of those three integrals using a u substitution. So the antiderivative of the first one is going to be the natural log of the absolute value of 2x divided by 2, or multiplied by 1/2. The integral of the middle function is going to be the natural log of the absolute value of 10x minus 5. And again, we would divide that by 10 or multiply by 1/10. And then minus the natural log of the absolute value of 10x plus 20. Again, we would divide that by 10 or multiply by 1/10, and then add the constant c in at the end. And when we look at those two antiderivatives, like those two antiderivatives look completely different. And both of them, like mathematically, we've done correctly. Okay, so you guys don't need to know this. Like if you guys get either one of these two, you're good to go. Okay, me grading this problem, like if this were on a quiz or on a test, like I would need to know that these two antiderivatives are in fact the same. So I'm going to explain why they are in fact the same. When I take the antiderivative that we came up with on the right-hand side, I'm going to use my log properties to rewrite each of these integrals here. Okay, so when we have 1/2 the natural log of the absolute value of 2x, I can use my log properties because the argument is 2x. I can separate that into the natural log of the absolute value of the numeric factor 2. So the absolute value of 2 is 2. So I can rewrite that as the natural log of 2 plus the natural log of the absolute value of x. So again, if I'm multiplying in the argument, I can separate that into 2 logs by adding those 2 log expressions. Okay, I can do the same thing for the middle log. So I pull 1/10 out front, and I can separate that middle log into the natural log of the absolute value of 5. And again, because 5 is positive, the natural log of the absolute value of 5 is the same thing as the natural log of 5, plus the natural log of the absolute value of 2x minus 1. And then I'm going to do the same thing to separate that third log into 2 log expressions. So I pull negative 1/10 out front, and I can separate that into the natural log of 10 plus the natural log of the absolute value of x plus 2 plus c. Okay, so what I did in the next step was I distributed 1/2 across the first 2 terms, 1/10 across the next 2 terms, and negative 1/10 across the last 2 terms. And then I just reordered the terms here. Okay, so I took all of the terms that have an x in them, so I highlighted those in yellow. I listed those 3 sets of terms first. So we have 1/2 the natural log of the absolute value of x plus 1/10 the natural log of the absolute value of 2x minus 1 minus 1/10 times the natural log of the absolute value of x plus 2. And then I took the 3 constant terms and highlighted those in blue, and I listed those 3 terms next, okay, which is 1/2 the natural log of 2 plus 1/10 the natural log of 5 minus 1/10 times the natural log of 10. And then what I did was I took those 3 constant terms in purple and I added that to my constant c. And then I renamed that constant c sub 1. Okay, so again, when I take those constant terms and add them to c, those are all still part of a constant, okay, which I renamed as c sub 1. And when I do that, now we see that the 2 antiderivatives are in fact exactly the same. Okay, so the 2 antiderivatives that we boxed don't look the same at first glance, but with some algebraic manipulation, they just differ by the value of a constant. Okay, so a really interesting example, and just curious, I mean, I would venture to say that some of you guys probably worked it out the way on the left, some of you guys probably worked it out the way on the right. Again, I would recommend you work it out the way we did on the left-hand side. Like I said, I just think it makes the calculus a little bit easier for you. Okay, so again, I just didn't feel like writing all this stuff out a second time after the video froze on me the first time. So yeah, hope you guys have a great rest of your day. We'll see you guys in class either tomorrow on Tuesday for period 2 or Wednesday for period 5. So hope you guys are doing well. Take care. Bye.